Okay, good morning, everyone. Today we'll begin our exploration into exponential functions. So we just got done with polynomial functions. Now we're going to go on to exponential functions. The COVID-19 pandemic in the United States represents a good illustration of exponential functions. February 28th, we had a total reported cases of 60. By December of 23, there was a total of 21,113,528 reported cases of COVID-19 in the United States. We will say that the total number of reported cases of COVID-19 in the United States grew exponentially over that period of time. Okay, and we'll take a look at what exponential functions are. Now, let me ask you this: If would you rather have $10 million today, or the value of a penny that doubles in value each day for 31 days? So on the first day you have a penny, next day now it's worth 2 pennies, the next day 4 pennies, and the next day 8, and so on and so forth. What would you rather have? $10 million today, or the value of a penny that doubles in value each day for 31 days? We'll answer that question. Okay, we'll come back to that. All right, so let's take a look at what exponential functions are. So today we're going to write and evaluate exponential functions to model growth and decay. Some vocab here. What's an exponential function? We'll talk about the base, but I also consider the multiplier, asymptotes, and then exponential growth and decay. The general form for an exponential function is this here. F of t is equal to a times b raised to the t, or f of x is equal to a times b raised to the x. T stands for time. A will be the initial amount, that's when time is 0, and b is the base or the multiplier. We generally like to look at exponential functions in terms of time because that's where it makes more sense. So if I go back out to the total number of reported cases of COVID-19 in the US, you can say, we would say it grew exponentially over time. So we generally like to use t rather than x for exponential functions. So let's take a look at how we write exponential functions for that form. F of t is equal to a times b raised to the t. Well, here I have a table at time 0. Okay, I see that f of t or y is 10. Okay, so again, a represents the initial amount. That's when time is equal to 0 or t is equal to 0. So here, a then in this case is going to represent 10. That's my initial amount. Now my multiplier or my base, that's easy to get at. All we have to do is take the day ahead and divide it by the day behind for f of t, and we get our b. So what do I mean? So b then is going to equal, so if I take a look at time or day 1, okay, so that's 20, and if I divide that by the initial day, f of t for the initial day, which is 10, I would get 2. 20 divided by 10 is 2. And then I can do the same thing for the next one. I could go 40. F of t is 40 at day 2. And if I divide that by f of t in the prior day, which is 20, again, I would get 2. Or 80 divided by 40 equals 2. So that's my multiplier. That's my base. In other words, every time time increases by 1, we're multiplying f of t by 2, our multiplier, or that's our base. So b is equal to 2. So my function then would be f of t is equal to the initial amount 10 times my base, or multiplier 2 raised to the t. Okay. Now if I graph that on decimals, you'll see that it grows quite quickly. Okay. So y is equal to 10 times 2 raised to the x. Okay, so you see it's growing quite quickly. At time 0, we said at time 0, the y-intercept, my initial amount was 10. Okay, time 0. But then it grows exponentially. Okay. Now, I want you to notice, though, as I zoom in, I want you to notice that that function, y is equal to 10 times 2 raised to the x, is getting closer and closer. You see that red line is getting closer and closer to the value of y equals 0. Getting closer and closer to y is equal to 0. All right, and we would call and the line y is equal to 0 is like a boundary line. It's a line that the graph, this function, will never touch or cross. And so we call that an asymptote. So an asymptote it's a point in the coordinate plane that a graph approaches but never crosses. Well, that's not quite true, but it just it approaches that line, though the function will never equal 0. Okay, so that would be an asymptote. It's a line that a graph approaches but generally doesn't cross or touch. So this graph approaches the line y is equal to 0. So that would be an asymptote. Okay, so if I look at, so that was my function, and then my asymptote then. So that graph approaches the line y is equal to 0. So that would be my asymptote. Would be y is equal to 0. That's what an asymptote is. Okay, so let's do some more of these problems. Let's look at the next table. Here, at time 0, f of t is 3, so a is equal to 3. And then b then would be the value of f of t divided by the value before. So 9 divided by 3 equals 3, or 27 divided by 9 equals 3. And then so on and so forth. So my equation for this one then would be f of t is equal to my initial amount, which is 3, times my base, which is 3, raised to the t. And then one more. So this next table here, again, at time 0, f of t is 1, so a would equal 1. And then b would be the value of f of t divided by the value of f of t behind. So this would be 4 over 1 equals 4, or 16 divided by 4 is 4. So my function would be f of t is equal to my initial amount 1 times my base or multiplier raised to the t. And we could just write that for t. All right. So I want you to notice here, though, in this case here, my multiplier was always greater than 1. When that happens, so if I go back to my decimals here, so when that happens, as long as that multiplier is greater than 1, so here if I make it 4, you see it grows, and it grows even quicker. Or if I made it, what was the other one I had? 3. So 3 times 3 raised to t. Oops, let me go back here. Or 3 times 3 raised to t. Again, it grows. And so as long as the multiplier b is greater than 1, we have exponential growth. It grows as long as b is greater than 1. All right. Now let's look at where we have decay rather than growth. Here again I have a table. At time 0, f of t is 20, so a is equal to 20. That's my initial amount. But now notice then that if I take 10 divided by 20, that's a half. Okay? If I take 5 divided by 10, that's a half. So my multiplier, so I'm always multiplying by half. So my base or my multiplier is half. So my function is going to be f of t is equal to my initial amount, which is 20, times 1/2 raised to the t. All right, now let's take a look at that on decimals here. So if I go to decimals. All right, so there. So notice, so here, that's 20 times 1/2, or 0.5 raised to the t. But I want you to notice here, that blue graph, that's decay. Okay, so that graph, the value of f of t is getting smaller and smaller. Again, my asymptote will still be the line y is equal to 0, because you'll see that that graph is getting closer and closer to the line y is equal to 0. My asymptote will still be the same. But that's exponential decay. Okay, so as long as the multiplier is less than 1, so if I had like 0.02 or 6.02, it's really decaying. As long as it's less than 1, then I'll get decay. But then I have 0.5. I get decay. Okay, and then we'll look at the next one here. And then here, again, I have a table at time 0. F of t is 40, so a is equal to 40. And then if I take 10 divided by 40, that's a fourth. If I take 2.5 and divide it by 10, that's a fourth. So my function will be f of t is equal to my initial amount, which is 40, times my multiplier 1/4 raised to the t. And that would be decay as well. Okay? So here, so I gave you, we started with the vocab here. And how do you recognize exponential growth? As long as the multiplier, or b, is greater than 1, we have growth. If the multiplier b is less than 1, and b, the base will always be greater than 0. Okay, always. We'll never have a negative base. And we'll never have a base, or b, that's 0, because then we just wouldn't have a function, right? We wouldn't have anything. So if b is less than 1 and greater than 0, then we'll have exponential decay. So growth, b is greater than 1, decay, b is less than 1. All right, now let's look at some applications of exponential functions. Now, the next form that we're going to take a look at, though, before I jump into that, is it's kind of like the same form. This function is going to involve a percent. So we say f of t is equal to a times 1 plus or minus r raised to the t, where r is some percent. But we're going to have to convert that percent to a decimal. So when we go 1 plus or minus r, the r has to be a decimal. R is a decimal. So just to recall, how do you convert percent to decimal? So if you have 5%, that's 5 per 100. Oops, 5 per 100. And so you take 5 and you divide it by 100, and that will give you 0.05. If you had 1.25%, that's 1.25 divided by 100, and so that would be 0.0125. So let's look at this application. Tony purchased a rare guitar in 2000 at time 0 for $12,000. And then it's estimated to grow 14% per year. Use a graph to find when the value of the guitar will be worth $60,000. So first we have to write a function, exponential function. So we have f of t is equal to the initial amount, which is, they give us 12,000, times 14% as a decimal is 0.14, so it's going to be 1 plus 0.14 raised to the t. So we get our equation, f of t is equal to 12,000 times 1.14 raised to the t. I'll graph this. Okay, so we could estimate the value of the guitar like in 10 years. So f of 10 then will equal 12,000 times 1.14 raised to the 10th. And I'll show you how to do that with your calculator. So let me just do this, go to the calculator here. This calculator likes to blow up my machine sometimes. So that was 12,000 times 1.14 raised to the, where's my caret key, raised to the 10th. So the value of that guitar then would be worth $44,486 about. So 44,000 and what did I say? 486. About 486 bucks. Okay, but we want to know, when is the value of the guitar going to be about $60,000? So what I'll do is I'll use decimals to do this here. I'll show you how to do this using decimals. So this is, I have to just write down my equation, 1.14. Okay, so let's do this using decimals. So I'll go out to decimals, and where do I go? Okay, so let me clear out these functions. I don't need those anymore. What I could do initially, I could just graph the function y is equal to 12,000 times, what's that, 1.14 raised to the x. and that's my function. Because these things, they grow so fast, sometimes they're difficult to see. You kind of have to zoom in. But right there, you start to see the graph. We want to know when the value of that function, what did we say, when it's going to be worth 60,000, right? When will the guitar be worth 60,000? So again, I'll go back out to decimals. So we want to find out, well, we got to go to when y is equal to 60,000. This what makes this so difficult. Okay, there we go. All right. Now, as an approximation, okay, there we go, getting zoom in. So if I click there, we're 60,000. So it looks to be said, if you look down there, it says 12.254. In a little more than 12 years, okay, look at the bottom of the screen. It says 12.254 and 59771. It's in about 12.25 years. But there's another way we can get at that. So, and I'll show you. So if I click my plus button, and then I'll click my table, and then we have x1, and then for y1, we'll just replace. We'll put in our expression. Now, we're going, rather than using a variable x, though, we'll be using x1, because that's what our table is using, x1. So I'm going to type that in, 12,000 times 1.14, care key, raised to the x1, not x, x1. So there's my equation there, 12,000 times 1.14 raised to the x. Now what I can do, I can start to populate this table. So I'll put in 1, and that gives me the value of the guitar, 13,680. I'll press enter, I'll put in 2, and now that gives me the value. Then in 2 years, it's going to be 15595. And so now, because I inputted 2 and it incremented by 1, if I keep pressing enter, the computer is smart enough to know that I want to increment by 1. So I'm just going to keep incrementing until I get to more than 16 or 60,000 or 60. So you can see between year 12 and 13, the value. So after the 12th year, okay, the value of the guitar will be worth more than $60,000. So when will the when is the value of the guitar going to be worth more than 60? Well, between the 12th and 13th year. 12th and 13th year. Okay. And so let's look at another one here. So here we have the value of a truck bought new for $28,000 decreases 9.5% per year. 9.5% is 0.095. Write an exponential function, graph the function. Okay, so our initial amount is 28,000 and it's decreasing 9.5% again per year. So again, we have to change that to a decimal. So 1 minus 0.095 gives me 0.905. So our equation is going to be 28,000, which is my initial amount, times my multiplier, 0.905 raised to the t. I guess one way you could look at it like this here. If the value of the truck is decreasing 9.5%, then each year it retains 90.5% of its value. It retains. Graph the function. How long? And then it says, use the graph to predict when the value will fall to 5,000. Okay, so again, we'll graph that using decimals. Just let me write that down. That's 28,000 times 0.905 raised to the x. All right, and so we'll answer that using both the graph and the table. So I just need to change this here. So this is going to be 28,000. And then my multiplier is 0.905. Okay, and then I'll change my table here. So this is 28,000 times 0.905 raised to the x1. Remember x1. If I look at the graph, we want to know when the value of that truck was going to be less than 5,000. So again, I could use those, I guess, together. That'll be helpful because I'm looking for y is 5,000. Yeah, it's a little better. As you can see, the value of this, well, And maybe you can't see it, but it's a decay function because the multiplier is less than 1. So, but we want to go to where it's 5,000. I don't like using the graph, more like using the table. Okay, so, but anyway, here, if I just, so if I click here at about 5,000, yeah, so it's about 7.262. All right, but if I look at the table, and so let's see here, when did we get below 5,000? So, wait a minute. Oh, that was 28,000, wasn't it? Because I was going to say, didn't agree with the answer I just had. So, yeah, changing this to 28. Okay, now that's better. The table and the graph should agree. So it falls to less than 5,000 after the 17th year. And that's what the graph showed. So where was that? Oh, right there. 17.26 or something like that. So after the 17th year. All right, so they said at about 17.3 years. Okay, so that's an introduction into exponential functions there. So let's take a look at what we started here. So what would you rather have? If I go here, $10 million today, or the value of a penny that doubles in value each day for the next 31 days. Our equation is going to be f of t is equal to the initial value is 1 penny, and the multiplier is 2 is doubling raised to the t. Well, what is that going to be worth then, or just 2 raised to t? Well, what will that be worth then in 31 days? Well, let's see here. Use our calculator. What is 2 raised to 31? $214. So 21474. 21474. 83648. 83648. Well, that's how many pennies you'd have by the 31st day. Well, okay, that's how many pennies. There's 100 pennies in a dollar, so you would have 21474,836.48, 48 cents. So, what would you rather have? $10 million today, or $21,474,000 31 days from now? Okay. Provided you're going to be alive in 31 days, I will wait 31 days. Okay. Of course, it'd be nice to have $10 million either way. All right, so there. So that's an introduction into exponential functions there.